Renner. I am a data scientist here at Intersys, and I'll be talking about streaming data. Before I get started, though, I want to just say if you do have any questions, please put them into the chat window, and we'll go through those at the end and answer as many as we can. All right. Okay. So this talk is about streaming data. Primarily, I wanted to give an overview of it and give a sense. The main goal I had was to give a sense of the types of problems that are pretty trivial to do in batch processing, which is just all at once kind of historical processing. Problems that are trivial to do in that space are actually incredibly difficult in streaming, and there are a lot more things that that have to be considered when working with streams. So I said before, I'm a data scientist here at Intersys. You can find my GitHub at that URL, and code, including the code for this talk, is located there online, all open source, obviously. I do work for Intersys. You probably know already all of this, that we do consulting and staffing as well in the big data analytics and application development space. So that's all stuff you probably already know. So the one thing I wanted to do was walk through an example, like I said. So the main scenario we're going to walk through is this. Suppose that what we want to do is we want to compute the click-through of an online advertising campaign. And so the click-through is basically a measure of how effective an ad is at getting someone to interact with it. So if an ad is shown and clicked on, then that's considered a success. So click-through is basically the number of times that it was clicked divided by the number of times it was shown. I'll go through that in more detail in a moment. Essentially, though, it's one of the key performance metrics for online advertising. So why would you want this in real time? Maybe you're running a sophisticated live optimization scheme, and this is done in industry in several places. Or if you want to run a live A/B test and you want to do some peaking at your p-values, which is not a good practice, but people do it anyway. Or your executive was told to get this in real time, and no one really knows what that means. So we just get it as fast as possible. Any of those are a reason why you might want to look at this in real time. Some obviously more valid than others. But the click-through, as I said, is just the number of clicks divided by the number of impressions. An impression in this online advertising terminology is how many times the ad was shown. Basically, every time an ad is shown, that's called an impression. So that's the click-through. That is a really simple equation, right? So it's not that's not a hard thing to do in batch mode. So how would we solve it in batch mode? Well, there's a technology called Apache Spark. And what that is that's a distributed computing framework that operates in memory for maximal speed. And the primary abstraction in Spark is called the RDD, which is Resilient Distributed Data Set. And what that is basically is the data set that you have is too large to fit on one computer. So it's put across multiple computers on the cluster, and Spark handles the coordination of the operations that get done. Some of the computer nodes go down while you're processing. It handles, retasking the computations and all of that. And it has batch and streaming modes. For batch mode, you could also solve this with more traditional Hadoop-type technologies like MapReduce or whatever, but since this talk is about Spark streaming, I thought I'd go over it in Spark. So the batch solution, then, is going to be pretty simple, right? If you've got your inputs, say, to be just really simple about it, would be a session ID or maybe a unique identifier for a particular user, some kind of identifier that says this person or this session in the browser is what was shown this ad. And the same thing for clicks, but obviously there are going to be far more in the impressions column or in the impressions data set than the clicks data set. So what you have to do first is we need to roll up our impressions by counting them. And we need to do the same thing for clicks. We want to roll them up by ad ID because we want to measure the effectiveness of the individual ads that are done. So once you do that, that's just a simple group by in SQL. Then you join the two of them, and you get the ad ID, the number of impressions, and the number of clicks. And from there, you can calculate click-through. And that is really it. Like, that's all there is to it, to do this in batch. It's a simple ratio that involves counting things, and that is like literally what big data was built to do. So this is a perfect use case for that. It's got a lot of conveniences. So one of the conveniences, the data set is bounded, meaning there's not an infinite amount of data in it. It can be huge, but it's not infinite. You know ahead of time, this is how much data I've got, this is how many resources I'm going to need to allocate, and the computation is optimized to fit within those bounds. The other thing is the data is static, so there aren't additional things coming in while we're doing the calculation. We have basically a file, and it's not really changing while we're doing this computation. If we need to rebuild it, we're going to have to rebuild it off the whole file. When you put those two together, those first two together, what you're essentially talking about is a complete view of the data. Right? This is the total. I have my data in one bounded box, and that's it. That's what's there. And because we know ahead of time how much data we have, then all of the computational aspects that we're doing become much, much simpler. Streaming data, on the other hand, is unbounded. We don't really know how long the stream is going to take. I mean, in some cases there are some cases where maybe you do know, but in principle you don't. If the data is coming in from site traffic or something like that, unless you plan on your site going down, you really don't know, how long you're going to keep getting data, ideally forever. The other thing is the data is dynamic. There's constantly data being added to the end of the data set, or possibly the middle if you're coming in out of order, and we'll talk more about that later. But the point is the data is not static, and there's also an incomplete view because the data is dynamic and changing, and because we don't really know how much data there's going to be before the end, we don't have that complete view of the data when we're trying to do something streaming. So in terms of convenience, this is like the total opposite of batch mode. All of the things that we lean on to do batch correctly, we can't anymore. So that's where stream processing comes in. So stream processing is a really kind of exploding field right now. There are a lot. I've listed 4 stream processing frameworks here. There are 4 to 8 more that I just didn't have room to put. There are a ton, and new ones are coming out all the time, and that's because a lot of companies are starting to tap into the potential of stream processing, not just for doing data analytics and data ETL type stuff, but also to power applications and simplify the overall development process and flow in showing user-facing applications. So it's really coming together from a lot of places. So the top one there that I'm looking at is the top 2 are the ones we're going to be talking about. Those are going to be Apache Storm and Apache Spark streaming. The other 2 at the bottom, Flink and Samza, those are both also Apache projects. They're not as wide of use. Flink is very popular in Europe, and Samza was built out of LinkedIn. So LinkedIn is using it, and a couple of companies have adopted it for large-scale production cases. But by and large, the most of the market comes from Storm and Spark streaming. So I'm going to focus on those. So I'll talk first about Spark streaming. So the way Spark streaming works is it uses what are called microbatches on a continuous stream of data. Remember that I defined the batch processing as a whole bunch of records at once, basically. Microbatches are just like small collections of a small, and it doesn't necessarily have to be like small, but a number of records within a given time window. So if I say I want my data microbatched by 30 seconds, every one of these microbatches will have 30 seconds of data in it, and one of them won't stop. We won't start the next microbatch until the current one is already filled. So we'll wait 30 seconds and then go to the next one. It's all sequential. Each batch is an RDD. Remember I said a resilient distributed data set for the batch mode. So each microbatch that comes in, basically what it does is Spark Streaming just feeds it to the batch engine over and over again. And that's really at the core what Spark Streaming does. That's what it does. It just takes the batch mode and puts it in a repeat loop. That's a pretty powerful model. Let's take a look at the first crack at how we would do that. If Spark Streaming is really batch mode, then we could just put the batch solution on the RDDs, right? We have our user ID, or I think I called it session ID earlier. But we have our unique identifier. We extract the ads. We do our group by so that we count the number of ads or number of impressions or clicks, based on ad ID. Then we do our join on ad IDs to get the impressions and the clicks all in the same space and compute our click-through. So we can really just repeat the batch solution in the streaming mode. But does that really solve the problem? Well, there are a number of issues with that. The microbatch length has to be shorter than the time to click. That's a pretty big issue. If I have an impression and my microbatch window is 30 seconds, but it takes someone 1 minute to click, then their click is in another time window. That join's not going to pick it up, and each microbatch, what we compute as a click-through, is going to have bleed over from the sessions. You'll get a skewed sample. Statistically, it may or may not be. It may or may not end up being relevant. It's possible it could average out, but that's not a guarantee. So, and that's not a strong guarantee if your microbatch window is small. So if you don't want to do 30 seconds, you want to do 5 seconds or 1 second or a millisecond, all of which you can do. Then you could run into issues. So that's what we mean by the boundary loss. If the microbatch edges, you might have, that's a hard cutoff in our process. This also assumes the microbatches are ordered and guaranteed to be ordered in the same way. And if they're not exactly ordered, that's going to be a problem. So if your impressions and your clicks are giving you streams of data at about the same time, both in absolute real time, then great. You don't really have to worry about ordering. But if one of them's a little slower than the other sometimes, if they're part of a separate microservice or something like that, there's some latency, then this solution would be totally host. So the primary idea is don't cross the streams when you're doing Spark streaming. That's not really a good way to do that. In other frameworks, you're not even really allowed. In some other frameworks, Kafka Streams is coming to mind. You're not even allowed to do this without specifying a time window, which segues right into time windows. So windowing is the way that we solve this problem, right? We need a way to basically make our microbatches longer without actually, we need to have a bigger view, essentially, of what's going on in the data without making the microbatches longer. And the reason is microbatches are expensive. If you keep them around, or if they're too big or something like that, you're using a lot of resources, and it's taking a lot of processing power to make that work. Windows are a solution to that problem. So what a window does is they merge RDDs, essentially, from the D stream. And what I mean by that is it's basically an aggregation. A window is an aggregation that occurs over a finite amount of time. So what happens is new data comes in, old data rolls out of the window, and your aggregation changes and gets emitted as you go. So if I have 5 impressions in the window, 2 of them roll out, but 3 roll in, I'll end up with 6 after that, and that's what gets emitted as the aggregation. So you can think of a window as basically a view, a continuously sliding view of the stream. And this is the way pretty much every stream processing framework does this type of computation. In particular, if your aggregation is invertible, so in our case it is, it's counting, right? If I invert a count, it becomes plus +1 or -1, then I really only have to store, I have to store a lot less. I just need to store at each point what the aggregated value of the RDD was and roll that off at the end. I don't need to store every single element of the RDD in the window. So that's the difference. I can store an aggregated view in the invertible windows. So here's the way the rolling count, this is what that looks like, sort of up close. As the new RDD enters, it gets basically merged into the window, right? So if you imagine the window as a table where you've got an add ID column and a count column, when you bring a new RDD in, that aggregation gets updated into new counts for whatever the add is that you were shown. And also the old data rolls out. So the inverse of the operation also happens so that the window only has a finite memory. So one of the things you could do is say, I want a 1 hour sliding window that slides every 1 minute on a microbatch length of like 30 seconds or something. And that is a valid way to specify it. So we really have 3 numbers that we got to track when we're doing windows. In Spark streaming, you need the microbatch length in units of time. You need the total length of the window and also how often you want to slide it, which seems kind of complicated, but it's actually pretty intuitive once you get your hands on it. So if we want to do our join again in a way that is correct, what we do is we use the count by window and value method, and that may have changed. Spark changes its APIs pretty frequently. It's kind of hard to keep up with, but at last I checked, count by value in window is the actual name of the method, but there's probably some similar functionality if that's not like what it's literally called. Essentially, though, what that does is you specify the key and you specify the time window length, and it does that roll up for you. That's really convenient. It's a nice high-level operator. So we do that. We roll up our add IDs and count by the values and within the window. And the nice thing is that our window, when we zoom out and look at it, is just another RDD. Right? It's just a different way of, it's just a view, but it has all the same operations you can do that an RDD, that you could do to an RDD. So when you're ready to join, you could just join the 2 windows, and then you can compute your click-through. This basically is just going to be a sliding batch mode solution. So the idea is don't join the streams, join the windows, because the windows are bigger and they have more memory. So our total add ID click-through is going to be changing according to the sliding of the 2 windows together when we do the join. So for example, the one caveat here is our click-through is only going to have a valid number for however long the window is, right? So some things to consider when looking at this is that the solution relies on the processing time. This is the time that the events hit the system. It's not the time that the events actually come in or are actually produced. There's been a lot of work very recently, like last 6 months to a year, on getting processing, on making the time event time-based rather than processing time-based. That's really important and really difficult work. And I won't talk too much about it here, but that's something to note. If you've got data skew or extreme delays, there could be an issue. If it's extreme enough to get outside the window, you could be running into problems. A high-volume burst could conceivably crash the system. That's not very likely to happen, but Spark streaming runs off a Spark engine, and if you've ever used it, the out-of-memory error is just as real in Spark streaming as it is in batch Spark. So the other thing is that the latency and the window accuracy are very tightly coupled. So a shorter microbatch interval would mean that the window is going to hold more data. In our case, that's less of a concern because we are able to roll up and aggregate. Because it's invertible, we can store only the aggregate values. But in general, you may not be able to do that. And if that's the case, if your window gets too large, that could be wasteful, or it could be it could cause system problems and that sort of thing. So those are the types of things that you need to worry that you need to worry about when working with Spark. So that's basically the Spark solution. And before I move on to Storm, I will just say that if a client actually came to me and asked, how would you solve this click-through problem, I would probably go to Spark Streaming. Spark is part of every major Hadoop vendor distribution. The API is very high level. It's easy to work with. And from a configuration perspective and a tuning perspective, it can be a little frustrating, but it's not. It's very simple. Not a lot of code to manage necessarily, and it's everywhere. So I think for most use cases that aren't really going to push the limits of performance, I would definitely choose Spark Streaming. That said, when you have a real seriously high volume streaming problem, really high volume, you would use Storm. So for example, Twitter basically, Twitter bought Storm from a startup, but Twitter has the largest Storm production, or largest Storm deployment in production today, I believe. Although they've changed out the back end a little bit, they have a pretty serious streaming problem, and they have a lot of data that comes through, and Storm can absolutely handle it. So when you really want to push it in terms of amount of data and speed of the data, Storm is really where you need to go. So Storm's got a few big differences from Spark Streaming. So the primary one is that Storm deals with events one at a time. That's really important because the operations can be a little more difficult to write, and the code is a little. You've got to think about it a little differently because it's no longer a collection of things. It's what do I do when I get a new event, and that happens one at a time. The nice thing is you don't have to wait on the microbatch length either. So if you're getting 100 events a second, that's what you'll get with Storm. Whereas Spark Streaming, you'll get those events right when they happen at 10 millisecond level. Whereas with Spark Streaming, you're not going to get them until that microbatch length is done. The other thing is, rather than the data being distributed, in Storm, the units of computation are what's distributed. And Storm is pretty smart about arranging things across the network to make it all run. It has a pretty sophisticated resource manager. It's not really something you have to worry about. But when you need to increase the parallelism, you don't increase the parallelism of the data. You increase the parallelism of the operation. So if one operation is going slow, you can add instances to that operation and make it to help it go faster. The terminology around Storm is a little different. So data sources in Storm are called spouts. In ours, we have a spout for impressions and a spout for clicks. And here, we could do the aggregation first and then join, but I wanted to show a different approach. I don't necessarily recommend actually doing it this way in production, but it's a nice example that highlights some things that are much easier to do in Storm than Spark. And that's really what I want to do, is highlight the differences. You could easily totally replicate the Spark solution in Storm, and you'd be great. But I wanted to do some things a little differently. So we're going to join first, and we're going to join on user ID. If you're thinking about it a little bit, that's going to be a hairy join, but I'm going to show a way to do that pretty nicely. That join goes in what's called a bolt, which is a unit of computation. So a spout is a source, and a bolt is a unit of computation. And when you wire these things together into this graph, that's called a topology. So that's just Storm's terminology. So to do the join, let's take a quick first stab at it. If we hold a set of user IDs, then when the impression comes along, we can add it to our set, and then we can pass downstream that we've seen an impression with this add ID. When the click comes along, we can check to see if the set has the corresponding user ID, because we decided that we need to be much more accurate. Again, it's kind of an extreme case, but it's a nice example. We can check to see if we've seen the corresponding impression, and if we had, we emit the click event, and if we haven't, we hold it. in the set, so that when the impression for that user ID does come along, this would be the case of out-of-order data, it can go join, it can go grab that corresponding set. Oh, I've seen a click too. Let's emit both types of events so that we're not emitting clicks before the corresponding impression, and we're not holding up the impressions to wait for clicks. So there are issues with this set. It's not a really memory-efficient representation, which means that we have a limited amount of time memory to actually hold the user IDs. If every user ID is a UUID, for example, that's a big object. That's a string, right? Or a Java object. Either way, it's not small, right? And that means that we run the risk of running out of memory. Now we can scale out by just loading up the instances for the join and be done with it, but that's expensive, especially if you're running on a cloud or something. You don't really want to be paying for that if you could be smarter about the way that you write the code. So one thing that we could do about this is we can introduce a data structure called a Bloom filter. So a Bloom filter is a specialized probabilistic data structure. So what that is that's a data structure that doesn't necessarily give concrete answers. It will give you the right answer most of the time. What you get in return for sacrificing absolute accuracy is you get the ability to use way less memory. So what a Bloom filter will do is it will return true every single time that an element that you're asking it about is in the set, and every now and then it will also return true sometimes that an element is not in the set. And that has to do with the way the data structure is built. And there are ways to tune those rates as well. It's not a fixed thing. So if you really need it to be like 99% accurate or 95% accurate, you can trade off. The trade-off is the more accurate you are, the more space you're going to take up. But the cool thing is that the space remains constant as elements are added to the Bloom filter. So it's allocated once, and then that's it. And it's a much, much smaller amount of space than you get with storing just the objects. You can't retrieve the objects because you're not actually storing them. You're storing a hashed version of them. But you can test membership, and that's what we really need here. The other thing is eventually they do saturate, and they can become unusable where they're just going to return true every single time. That happens when you put too many elements in. There are ways around that. One of them is to swap out Bloom filters after a while. So after X number of elements, you can count how many are in there. You reach a certain threshold, swap it out for a new, fresh one. There are ways algorithmically of sort of decaying Bloom filters as well. So there are a lot of variants on this, but there are some the advantages far outweigh the disadvantages in this case, and that's obviously going to depend on how accurate you need this join to be. If statistically speaking 99% is good, then hey, it's all right. If you're doing something that's going to require, I wouldn't put bank transactions through this, for example, or any of these systems. But for our case, it works pretty well. So our join looks basically like the set join, except now we're checking against the Bloom filter. And that means that we have a lot less memory that we're using, and that means that we can make our join window much, much bigger. And that's the real strength of the Bloom filter, is when you relax the constraint of needs to be exactly right all the time, you get to do a lot more stuff with a lot less resources. All right, so to calculate the click-through, I said that what we do is we emit the event, the add ID and the event type after we do our join. Well, we still need to calculate our click-through. So what we need is some function that's going to take the add ID and the impression of the click and produce the click-through. Well, the naive approach would be to treat an impression as a 0 and a click as 1. That average, though, doesn't really work, and I'm not going to say whether or not that's the first thing I did, but if you get 2 impressions in 1 click and you do it the way I just described, you get 0.33, but the answer is actually 0.5. So you have to crack things open a little bit. To do it correctly, what you really need are the average impressions and the average clicks. The click-through is just the ratio of clicks to impressions. Then what you can take is the average number of clicks you've seen and divide by the average number of impressions, and you will get the right number. Right? So if we put that calculation just directly in, that's still got a problem. And the problem is that when we're streaming data, the most recent data is the most important data. Data from yesterday is way less important than data from today. If they're all of the same importance, you wouldn't be doing streaming. You could just do that in batch mode and not have to deal with all of the stuff that I've talked about so far. But if you want to treat the recent information as most important, then you need to have some sort of memory built into the answer. So windowing is one way to look at that memory. That treats every element as exactly equal within the window. And again, if a client were asking me to do this, I would absolutely just implement the window in Storm. But I want to show you a different way that Storm can do that is a lot harder to do in Spark streaming. You can pick an average that is a windowed average that's basically a continuously smoothed, exponential, we call them, moving average. And what that does is that only needs to store the last value it saw. So that means that for each add, we actually only need to store one number, as opposed to the window where we would need to store all of the time that we were aggregating by. This, we reduce it to one number. The downside is that this approach does expect completely in order events, but we have covered that to some degree in our join. It's not perfect, but it does a decent job. So that the formula for that is basically you multiply the incoming average and or the incoming value by some coefficient that tells you how much more important it is than everything else, and then you add the rest of the contribution after that. And that can be applied one element at a time and uses almost no memory. So to summarize the streaming click-through, we have two variables, impression and click. We set them to 0. When an event arrives, we set impression to 1 if it's an impression, and we set click to 1 if it's a click. Then we just update the moving average for each of those two, the clicks, each of the two, the clicks and impressions. And then from there, we can just divide them and get our click-through. And that's a really efficient, low-memory way of doing it. It's got its caveats, but it's one way to tackle the problem. So to summarize Spark streaming versus Storm, Spark streaming uses microbatches, and this means that it has what are called exactly once failover semantics. Now, it's not something that I have talked about. Is what happens when a computer in the system fails. What happens to that data? What Spark streaming can do is Spark streaming can just rewind and play that batch again, and everything will come out exactly right. Storm, on the other hand, Storm processes events one at a time and has what's called at least once failover. That means that if it dies, it's going to get replayed, but it won't roll back the changes from the last time either. So some things could be played twice. That's what we call it, at least once. Like, you're guaranteed to get it through, and maybe it will come through a couple more times. Some use cases require exactly once, and others require at least once, and it really depends on the nature of the problem. I think for what we are doing here, I would say at least once is good enough, because failovers don't happen that often, and the volume of events means that we're already aggregating them. So if we get one extra count in there, it's probably not going to matter that much. The other thing is the API level. I didn't really talk about Storm's API, but Spark's API expresses its transformation as operations on collections. So if you're familiar at all with Scala collections or some of the new Java 8 Streams APIs, Spark mirrors that, but it's all distributed in that sort of thing. It's a very high-level API. It's very straightforward to work with, and And for doing straightforward things like what we're doing here, it's great. For more complicated things, it can get cumbersome. Storm's API basically expresses the transformations as functions. So for each of those bolts and spouts, what you have to do in Storm is create a class that does the operation for you and inject the operation into it. There's a lot more code, but also a lot more control over what you do. You're not limited to these high-level operations. You can actually get down into the details and say, this is exactly what I want done, and this is exactly how I want my state stored, and all of that. You complete control in Storm. So that's a trade-off, and that's not an uncommon trade-off to need more code to get more control. The other thing I didn't talk about is where we're getting this data. So data sources for streaming data could be sensors, could be tracking programs, electronic monitoring, web logs, all of that. But the point is, for data streams, they're almost always coming from somewhere else, which means that if you're connecting your streaming job directly to the source system, there's no back pressure between. If your streaming job is slow, what is that going to do to the source system when you get a burst of data? Right? Well, the worst case scenario is you plugged into a production server and your job hangs up and crashes to the production server. That's a worst case scenario, but when you're connecting directly to the data sources, that's always possible. The other thing is there's no standardization. So across an organization, you've got a whole lot of different systems that need to be put together. You don't want to be connecting to each of those individual source systems with each of the individual streaming jobs. That's kind of a nightmare. That's a different kind of stream crossing than what we're talking about with Spark, but it's still not recommended. So LinkedIn had this exact problem some time ago, and they decided to solve it. The way they solved it is they created something called Apache Kafka, which is open source. It is a distributed, publish, subscribe system, and it's implemented as an event log. You'll see why in a minute. The idea is that the consumers, rather than Kafka pushing data to the consumers pull data and track where they are in the log themselves. That means that the number of consumers is basically decoupled from Kafka itself. You can get huge scale out for reads. There can be thousands and tens of thousands of Kafka consumers. It doesn't really matter. Kafka is not really tracking them very much. So the primary abstraction in Kafka is called a topic. It's basically a log. And for whatever reason, I decided to make time go from right to left here. I'm not really sure what I was thinking, but essentially the new data is there on the left and it's coming in. And you could have a consumer at the latest offset, right? And that consumer knows where it is. Kafka does not know or care where it is. You could have another consumer in a totally different spot in the log, and it's fine. This is different from a traditional messaging system, which actually tracks which consumers are looking at it. Kafka removes that. Old data eventually gets removed or compacted, and new data, as it comes in, the consumers can keep up, and they'll wait until new data arrives. So each topic is distributed amongst a certain number of brokers, which partition the data across. That's going to determine the parallelism of however you read. So if I have one topic that has 3 brokers, then the parallelism of the streaming job that comes in is going to have 3 basically computers assigned to it. And from within that framework, you can repartition and redistribute as you need to. But sort of the limit for reads is going to be the limit of the partitions in the topic. And so the idea is the streams come in and add new data, and as that happens, that then gets pushed to the stream processing, or that gets put onto the log, and the stream processing framework reads the next batch in the case of Spark streaming, and this rolls along. What's cool about it is that the topics don't really care who's subscribing. So if you have, so what Kafka really does that makes it incredibly important is that it decouples the producers, the sources of the data, from the consumers. The sources, they just put the data on the topic. They don't really care who's reading it. the consumers, they read from the topic, and they don't really care where it comes from. Now, there's some things around things like schema management, for example, like what do these messages look like? How do you coordinate that? That need to be addressed that aren't in the way that I'm showing it, but there are tools for doing that as well to make sure that everybody's looking at the right version and that kind of thing. But essentially, this enables people to consume the data however they want without having to go to the source system owners or putting any burden whatsoever on the source system. So that means, like, in my opinion, that Kafka is the most critical part of any streaming data architecture. I haven't yet seen, as a consultant, any customer that we have had that does streaming data that doesn't use Kafka. It's really, really important for doing that and for doing streaming data in general. It's really the long pole in the tent of the whole architecture. And the nice thing is it's so simple, right? It's just a server. It doesn't need Hadoop to run. You just need to set up the brokers and do it. You can spin it up in Amazon Cloud. There are also hosted offerings. So, for example, MapR Streams and Amazon Kinesis, AWS Kinesis, both mimic Kafka. So there are options. And I think there might be some differences with MapR Streams. So, yeah, maybe don't quote me on that. But Amazon Kinesis is basically a clone of Kafka that's managed. So I guess to wrap things up, even problems that are trivial, remember, we started with we needed to count two things and divide them, and we ended with exponential moving averages and all kinds of crazy stuff. So even trivial problems have to be really carefully handled when you convert them to streaming. Windowing, when you're doing Spark streaming, is basically batch that moves, and that's really convenient because batch is very simple, and that makes the way that Spark streaming does it really simple. Storm requires a lot more work, but you could do a lot more with it. You could do a lot more. It takes a lot more code, but the control you have is really powerful. Kafka, where Kafka fits in is that it decouples the sources from the processors and acts as sort of a centralized, almost like an analogy to a data warehouse, but for streams. The other thing that Kafka does is it has excellent data resiliency. Everything in Kafka is replicated. If a broker goes down, it is not a big deal to just move that partition to another broker and keep serving it. It's also a natural back pressure mechanism, right? If you get a huge burst of data from the producer, the consumer doesn't care. The consumer will just keep reading from the topic and it'll be fine. So Kafka is I can't overstate the importance of how Kafka fits into the whole picture. So there's a lot of really new stuff going on with streaming data. Apache Beam is a Google's Cloud Data Flow SDK. So Google's Cloud Data Flow is a hosted offering on Google Compute Cloud that enables you to build similar directed graphs to do batch or streaming. What's cool about Beam is that it works with event time, and it has very strong consistency semantics. So remember I talked about processing time is when it hits the system. Event time is when it happened. Cloud Data Flow, or Beam, has event time-oriented semantics. It's really, really cool. Flink is the technology has apparently been around for some time, but it's only just now gaining traction. It's very popular in Europe. It is event-based, so it's not microbatch. It's one event at a time. But it also has that collection-oriented API that makes Spark so nice to code for. It provides extremely strong consistency guarantees and event time processing. So Flink allows exactly once with event time, or at the very least, that's on the near-term roadmap. I can't remember if that was actually done or not. Kafka Streams is a new library that came out this past May from the creators of Kafka. That's a kind of a different take. It's not a framework. It's just a library. So you can run that in any environment you want. It's like a WAR file or on a laptop, or you could do something like Docker or that kind of thing. And it just wants, so it doesn't attempt to solve the resource management problem like the other frameworks do. Storm hit 1.0 earlier this summer, and it added a lot of really cool stuff. It added windowing and managed state for stronger consistency and failover. A lot of really nice stuff. I haven't gotten a chance to work with it yet, but from what I've read, it's pretty cool. So I want to give as thanks to this talk for other consultants at Intersys, Raj Kalluri and Chris Gerken, for their inputs on this. And for references, you can there's code examples here. The Storm is written in Clojure, and the Spark streaming is in Scala. And you can hit any of those URLs to get to more information about it. Databricks is the commercial steward of Spark, and Kafka, or Confluent, excuse me, is the commercial steward for Kafka. So those companies are run by the creators of those technologies. So their blogs have a lot of great stuff in there. Anyway, that's all I've got. I'm going to take a look at the questions now. All right. Well, so a couple of questions that do occasionally come up, typically centered around where does Kafka really fit? Like where do you physically deploy Kafka? Typically, from what I've seen or read, Kafka is often deployed as a standalone resource because it is very intense and moving a lot of data through. So it's usually co-located in the data center, but it's like not in the cluster. So if you've got a big Hadoop cluster, the distributions do come with Kafka built in. But if you're running a lot of data through it, you kind of don't want Kafka running next to all your other stuff because it uses a lot of machine resources. So that's something that does come up periodically from time to time. If there are any other questions, just drop them into the chat window. So another thing that some people ask is how do machine learning and data science kind of fit into this? Most of that is all done in batch mode currently. Spark does have a really powerful machine learning capability on very large data sets. Flink does too. And the idea there is you train the model. That's usually done in batch mode, and then it gets deployed in streaming. So one of the things that you could do is export the model to PMML, that's predictive modeling markup language, and there's a Java library that you can read that. If you're doing Storm, that's kind of how you have to do it. It's like it'll take the model and it'll make the predictions in real time. It's not really training in real time. The other way you can do it is if you're running Spark in batch mode and have a streaming context in there too. You can serialize a Spark machine learning model and use it in a Spark streaming job without having to export it or whatever. And that's really, really handy. That's something that's pretty new in the Spark project. So I do have a question. Please elaborate a bit on how windowing is batch processing. So what I meant by that was that windowing basically creates maybe like I guess we call it a macro batch. Windowing is an aggregation that occurs, but only over a small subset. But it's the same kind of aggregation you get with batch mode. So contrast that with the Storm approach that I showed where every event changes the average as it rolls along. In a window, it's literally you get the same answer if you took that window, made it a CSV file, and ran a batch operation on it. You'd get the same thing. So that's what I mean by windowing is batching. It's just grouping the data together and aggregating on a smaller group. The difference being windows stay essentially open and they just slide along the new data. So in a batch, obviously, data doesn't really roll out, right? But in a window, it does. So that's what I mean. It's kind of like a moving batch is the way I think of it. Maybe there's a better way to explain it. That's kind of what's in my head. Okay. So any other, is there any? So got one question, is there, how do we accept the idea that the data is stored efficiently but with losses and eventually saturated? So one of the ways that does tend to be a problem if you have to be exact. The problem you run into is the more exact you need to be about your data in a stream, the more resources it's going to take, and the more latency you're probably going to have. right? So there is a trade-off in accuracy. One of the solutions to that is something called the Lambda architecture. It's a term coined by Nathan Mars, who created Storm. And the idea behind that is you actually have two systems running. You have a streaming system that has all these approximations and approximate algorithms that get the data there as quickly as possible that's almost right. And that gets backfilled by a batch system that's basically running the same code, but in batch mode you're always exactly correct. So the downside to doing that is you have two separate code bases you have to maintain. And Twitter, which Nathan Mars worked for after they bought his company that had built Storm, Twitter, the way they've created tools to actually take cascading jobs, I think, or maybe it's just MapReduce jobs, I don't remember, but turn them into Storm jobs as well. So they have code that you push, you hit a button and you get Storm code that executes in streaming and code that executes in batch at the same time. And that was their solution. Spark Streaming solves that by basically making the streaming operations almost exactly like the batch. So maintaining two code bases that are both Spark is pretty simple because they look almost exactly alike. The other solution to that Jay Krebs, who created Kafka, has suggested is to just replay the data. If the data arrives late, if you want an exact thing, you can just replay. One of the things about Kafka is you create a new consumer and just replay all the data that went through that topic and get the exact answer that you want. So both of those are pretty valid. Personally, I think Jay Krebs' solution of replaying the data makes a little more sense, but the Lambda architecture has been used pretty successfully and it's somewhat popular. So another question, do we need to hold the results for machine learning on real-time? Oh, sorry, wait a minute. One up. What's the best backend database for syncing with Spark Streaming? So I don't have a huge amount of experience with that directly, but it has been done with Cassandra, and I know HBase is also popular. Any of the big key value stores, I think, work pretty well for doing that. So yeah, when my colleague Raj Kalluri has actually had to do that, and he's doing it with HBase, and that's worked out okay. It's a little weird to do at first, but it seems to work pretty well. So, all right. So everybody who is on the call will get a follow-up email with the recording and the slide deck. And, thanks for listening, and thanks for your questions.
Thank you. Please stay